Hi, chemistry students. This is your lesson on electron configurations. Where are those electrons going to be? And this is part 1. So in a previous lesson, we talked about the development of the atomic model. And we're particularly going to focus on the last two models we talked about, which is the Bohr model, represented by this sort of solar system, and the modern version of the atomic model called the quantum mechanical model, which is symbolized by these clouds of electrons. Now, both of these models are pretty useful, but the Bohr model and its way of looking at the electrons in the atom has limitations, and therefore was not used in modern theory, but it does have some things that help us understand the modern theory, and so we are going to talk about it for a minute. So the main difference between the Bohr model, which is called the planetary model, and the modern quantum mechanical model is where how we visualize something called energy levels. Energy levels are where the electrons can exist outside in the space that the electrons occupy. And in the Bohr model, the planetary model, that space was very defined paths, like planets going around a sun or a solar system. And the problem that ultimately failed the planetary model, even though it had the idea that the electrons had to possess certain energy and therefore could only be in certain spaces and possess those certain amounts of energy, was that in terms of the mathematics, it only was very predictive for hydrogen. And as you know, hydrogen only has one electron. So that made it very limited. So these orbits were abandoned later on when there was a lot more math going on, which we're not going to get into thinking about these energy levels as being divided into orbitals. Notice the difference. And orbitals were more like areas of space, regions of probability, places where electrons with a certain amount of energy would probably be. Not random spaces, but just not very defined paths. They were more like clouds, regions of space. So the quantum mechanical model, which was first derived by a man named Erwin Schrödinger in the 1920s, is a set of complex mathematics that describes how electrons move in an atom. And instead of thinking of electrons as moving in defined orbits like planets around the sun, he described orbitals as areas of probability, sort of clouds, areas that the electrons would occupy rather than these definite paths. So if you look at the two beside each other, and the Bohr model, again, is another name for it is the planetary model. It said that electrons did have to have discrete energy levels, specific amounts of energy, so that they would stay out of the nucleus, because electrons are negative and the nucleus was positive with protons. And in order not to fall into the nucleus, because opposites attract, electrons had to exist on these discrete energy levels. However, the way they saw these energy levels was different. So in the planetary Bohr model, electrons moved in a specific path around the nucleus that they called orbits. So it was sort of the electron path model. The quantum mechanical model, which we abbreviate here as QMM, the path of the electron is determined by statistical probability. It was more like a cloud, like an area, as opposed to a defined path. And we called these areas orbitals. Now, if you're following along on my notes, there's a blank periodic table. I want you to skip that for now, and we're going to fill in the regions that talk to us a little bit about what is an orbital, okay? So those circles we saw in the Bohr model were sort of the energy levels, the principal energy levels. And in the quantum mechanical theory, these principal energy levels were actually divided into sublevels. So each principal energy level, each what you would think of as like the first orbit or the second orbit in the planetary model, was actually a little more complicated and divided into sublevels. Now, each sublevel is divided into orbitals, into these particular representations of space where the electrons would probably be. Now, these sublevels within the principal energy level are different shapes, and they represent, when we're talking about them, when we're really trying to tell people where the electrons are, we represent these different kinds of orbitals and their different shapes by letters, S, P, D, and F. Now, each one of these little orbitals that are in a sublevel, that are in a principal energy level, see how much more complicated this is, can hold up to 2 electrons of what they say opposite spins, and they are represented by up and down arrows. So again, let me just show you the difference. So let's just talk about like the first energy level. Whoops, the first energy level. So the first energy level in the Bohr planetary model, like for example for the 2 elements of helium, would just be a circle, and those 2 electrons would be going around the nucleus of helium in a defined path. But the first energy level on the quantum mechanical model, you'd still have the nucleus, but instead of going around in a defined path, there would be a cloud of negative charge, just 2 electrons in this spherical space. This is the first orbital in the quantum mechanical model and the first energy level. And this spherical space, somewhere in there would be 2 electrons. All right, so again, let me just sort of give you a contrast. In the Bohr model, this might be the first energy level and then the second energy level and the third energy level where the electrons would be. In the quantum mechanical model, the shapes where these electrons would be would not just be like one following the other in these defined paths, but would be in these spheres or in these what are called dumbbells. So the first 2 energy levels of the Bohr model would just be 2 circles. The first 2 energy levels in our modern thought would be that the electrons in the first energy level would be a small sphere, like here, and if this were the nucleus, and they would be somewhere in there, 2 of them. And then the second energy level would actually have 4 parts. They would have a sphere where 2 would be, and again, that would be an S orbital, and then there are 3 what are called p orbitals, and each one of these p orbitals would be sort of a dumbbell shaped along each one of these axes in 3 dimensions. And again, the nucleus would be right here at the origin, and 2 electrons could fit here, 2 electrons could fit here, and 2 electrons could fit here. So instead of being this nice, neat, like, oh, let's look at the first 2 energy levels as 2 little circles, this would be the first 2 energy levels. And in each one of these areas that I show you here, you would have 2 electrons. Okay, now we need to, before we get a little bit more into this, we need to just define the 3 rules that electrons follow about where they can go. All right, and we're going to write those. So the Aufbau principle says that electrons fill the lowest energy orbitals first. So they are lazy. We call this the lazy Tennant rule. Now, the lowest energy orbitals are closest to the nucleus because you need the least amount of energy to get the least amount of distance away from the nucleus. So when we start actually telling the electrons where to go, which will happen in our next lesson, we need to always remember we're always going to fill the lowest energy orbitals first. So the orbitals that are in the first energy level will fill first. If they get full, then the orbitals in the second energy level will be filled. If they get full, then in the third energy level. Now, as I mentioned to you, these little spaces in the energy levels and the sublevels can only hold 2 electrons. And we represent those 2 electrons with arrows. And we represent the orbitals, instead of doing spheres and weird dumbbell shapes, as boxes. And those 2 electrons have to be represented with up and down arrows because they have different spins. And when you take more chemistry, you'll learn why that is important. Anyway, that's called, the Pauli exclusion principle, because you can only, once you have 2 electrons in there of opposite spins, no more can go in. All right, last rule is something called Hund's rule. Now, within a sublevel, place 1 electron per orbital before pairing them up. And we also call this the empty bus seat rule. Now, you remember from previous slide that the p orbitals were, there were 3 of them. 1 going on the x-axis, 1 going on the y-axis, and 1 going on the z-axis. And so within that p sublevel, where you had p orbitals, you had 3 different spaces. And again, according to the Pauli exclusion principle, if we have to place electrons in those spaces, we need to spread them out rather than pairing them up first. Again, as we talk a little bit more about this in our next lesson, I think you'll see the implication. So this when we do our what are called orbital diagrams, would be an incorrect placement. All right, this would be the correct placement. All right, now let's go back to that blank periodic table and I wanted you to write a few things. So we're going to number the rows in that blank periodic table that you have on your notes. Or if you don't have the notes, just note that each one of the rows in the periodic table are numbered, and those big numbers, the 1, the 2, the 3, the 4, the 5, the 6, and the 7, are the energy levels. They're sort of equivalent to the first circle, the second circle, the third circle, and so forth on the Bohr model. So go ahead and fill those in and note that the numbered rows are the energy levels. Now the letters S, D, P, and F represent the sublevels. And so you can see in the first energy level, we only have one sublevel. It's a 1s. But in the second energy level, we have both 2s and 2p. So they're both on the second, like in the second circle, but there's some different areas of the second circle that we're going to talk about. All right, and the third energy level, you'll notice we have both S and P. Now, when we get to the fourth energy level, we actually have something called d orbitals. And then when we get to the sixth energy level, we actually have things called f orbitals. They're just different areas around the nucleus. Now, the other thing I want you to note is that, again, each energy level is this big number, and they correspond to the row. So you can know where the electrons are based on what row each of these elements are in. Okay, so again, this area is the S, this is the P, this is the D, and this is the F. All right, so let's go into these a little bit more. So letters refer to the shape of the orbitals in the sublevel. If you notice, you have, if you go back to your notes, under Hund's rule, there's a summary table of shapes and sublevels. So the s orbital, which is a sublevel, and you find an s orbital on every energy level, the shape is a sphere. The number of orbitals we have is just 1 per energy level, and then the max number of electrons in each S sublevel is just 2 because there's just 1 orbital. So you'll be filling in, filling in the table that's a summary table of the shapes of sublevels. Okay, so one s orbital has 2 electrons, and it's a sphere around the nucleus being at the intersection of these axes. All right, the p orbitals are groups 13 through 18 on the periodic table. So the p orbitals are dumbbell shaped. The number of orbitals per energy level is 3 per energy level, and the maximum number of electrons is 6. So in other words, these would be the p. You'd always have 3p. You'll notice 13 through 18 is 6 elements across. It helps you remember how many electrons. And remember, the reason why the number of orbitals is half is because each one of these can hold 2. So there are 3p orbitals that can hold 6 electrons, and their shape is a dumbbell. All right, now they're the d orbitals. The d orbitals start to get weird. They don't appear actually until the 4th energy level. And so they're filling in spaces. Remember, as you get higher and higher, these orbitals get bigger and bigger and further away. So their shapes sort of fill in some of the cloud area. And their shape, there are 4, and again, this is all mathematics. Don't try to figure this out. But there are 4 d orbitals that are clover-shaped and one that is a ring. They correspond to electrons filling in the transition metals, which are group 13 through 12 on your periodic table. You'll notice there are 5 of them, and if you count the number of elements between 3 and 12, they're actually 10. So the maximum number of electrons are 10. Each one of these weird shapes can hold 2 electrons. So 5 d orbitals for every energy level where there are d orbitals, and they hold 10 electrons. And then finally, they are the f orbitals. They're the rows at the bottom, the lanthanoid and actinoid series. Their shapes are, I like to call them 4 starburst and 3 ring bubble. Again, they don't have sort of well-defined names, but that's sort of what they look like. You'll notice there are 7 of them. They correspond to the lanthanoid and actinoid series, which are those 2 weird rows on the outside of the periodic table at the bottom. You'll notice the lanthanoid and actinoid series are actually 14 elements long, so they hold 14 electrons. But remember, every orbital within sort of these sublevels, within these energy levels, can hold 2. So you have 7 orbitals. All right, so just to summarize, the S sublevel. So we have the energy levels, but the energy levels are divided into these sublevels. And the S sublevel, which corresponds to filling electrons for groups 1 and 2 on your periodic table, the columns on the periodic table that are groups 1 and 2, are spherically shaped. They only have one sphere, so they can only hold 2 electrons. P orbitals, which correspond to electrons filling in the groups 13 through 18, and again, remember the groups or the columns, are dumbbell shaped, actually 3 dumbbells, and the maximum number of electrons is 6. The D electrons, those filling in the transition metals, which is groups 9 through 12, are 4 clover and 1 ring. There are 5, and the maximum number of electrons is 10. And then the F, which are those lanthanoid and actinoid, are sometimes called the rare earth, are 4 starburst and 3 ring bubbles. There are 7 orbitals, and the maximum number of electrons is 14. Now in my class, I am going to have you do a little summary reading with your assignment, and you're going to take an exit ticket for a classwork grade. We will finish part 2 of this lesson tomorrow. So thank you for listening.